So in this video, I will present two examples of perturbation theory's application. They both can be referred to as Stark effects because we will discuss the effect of external electric field on the energy spectrum of a one-dimensional harmonic oscillator and the hydrogen atom. The first example will deal with the non-degenerate perturbation theory, and the second example, that is the Stark effect in hydrogen atom, that will deal with an application of the degenerate perturbation theory. So let's begin with the Stark effect in 1D harmonic oscillator. So suppose we have a one-dimensional harmonic oscillator, so its potential is half m omega naught square x square. So this is its potential energy, so it's placed in this parabolic potential. And on top of it, suppose we apply an electric field which is directed along x-axis. So we're taking 1D case, so there's only one axis. So electric field is, its magnitude is E, and it's directed along x-axis. So it's I hat. So if this is the electric field, and suppose the charge is Q on the particle, it means that the force on this particle is this, and if this is the force, the potential energy due to this electric field, which is defined as it's defined as such that the force is negative of the potential. This would mean that the potential is minus, and this del is nothing but partial by partial x right now. So if V is Q E x, then we can see that if I put it here, the partial x of would be 1, and it's along x-axis, so I hat, so this minus minus plus, so I get this force. So this is the electric potential energy. This is the potential that the particle is already in. It might be maybe due to a spring sort of or some other force on the particle. So now the total Hamiltonian of this particle is kinetic plus potential energy, which is px square to m plus half m omega naught square x square minus qx. So we have a 1D harmonic oscillator which is placed in an external electric field along x-axis. So this is its total Hamiltonian. By the way, this happens to be a Hamiltonian that can be solved exactly in itself, but for the purpose of illustration of the non-degenerate perturbation theory, we will find the eigenenergies for this operator, for this Hamiltonian using perturbation theory. So clearly we can divide this Hamiltonian into two parts. So this H0 is this part. We already know the solution of this part, and this H1 is this external and additional term minus QEX. For H0, let me just recall that we have already found its eigenstates, which are numbered by n, and its eigenenergies are n plus half by s. So this is our spectrum of the unperturbed harmonic oscillator, so to say, which is the solution of this H0 part of the Hamiltonian. For H1, and we already know that this energy, if I label it E and 0, is different for each state n. So this is clearly a non-degenerate case. And to find H1, we recall that En1, the first order energy correction, is defined as N H1, and it was phi N0 when operator there. So here, if you want to compare with previous symbol, phi N0 is this number state N. Now let's compute this thing. H1 is minus QE. This is a constant, so I can take it out. And here it is X hat. So this X, let's call it X hat, and this is X hat squared. Now this X hat operator, we can express it in terms of raising and lowering operators, because this is equal to H over 2m omega naught square root A plus A dagger, because this X is equal to this into A plus A dagger. So this I can quickly write like this. So this will become N plus N A dagger N. Now this is a lowering operator. If it operates, let's say, on this thing, we will get N minus 1. This is a raising operator. When it operates on this one, we get N plus 1 squared and since these are two different orthogonal states, this inner product is 0, this is 0, so the first order correction to the energy is 0 for the one-dimensional harmonic oscillator. So let's try to compute the second order energy correction, because even though it's an infinite series, but sometimes we are able to compute it. And just to recall, the second order correction was sum over all k other than n was phi k0 h1 phi n0 mod square en0 minus ek0. So let's compute these terms, phi k, phi n. So phi k is nothing but our kth numbered state, and phi n, when we use this label, and now this is again minus qe into x hat, and for x hat, let me substitute h over 2 and omega naught k a plus a dagger n. So minus qe h cut 2 and omega naught, this becomes k a n k a dagger e h dagger 2 m omega naught. When this a operates here, it becomes n minus 1. We get n square root here, n minus 1. Similarly, here we get n plus 1, k, n plus 1. However, this k is going from 0, 1, 2, 3 up to infinity, and this is n minus 1 fixed, this is n plus 1 fixed. So this is 0 everywhere except when k is equal to n minus 1, and this is 0 everywhere except when k is equal to n plus 1. So in all of this series, there are actually only two terms when we have a non-zero term. So the first term is when k is equal to n minus 1, because in that case, when k is equal to n minus 1, this would be 1, and we get k h1 n as minus qe n square root h cut 2m omega naught. And when the next term is when k is n plus 1, in that value of k, this becomes minus q e n plus 1 is 2m omega naught. Let's now substitute these in this series and we get en 2. The first term is the square of this divided by en this. So square of this is q square e square m h cut over 2m omega naught, and then en, and this was the term for n minus 1, and k's value is n minus 1 plus the next term, which is non-zero, is for k is equal to n plus 1. We take the square of this, which is q square e square n plus 1 h bar by 2m omega naught over en minus en plus 1. Because for k is equal to n plus 1, this term is non-zero. Now this en, so what we get is we can actually take q square e square h bar over 2m omega naught common, and we are left with the n over en is n plus half h cut omega, and this n minus 1 is n minus 1 plus half h cut omega. So h cut omega is common, plus we are left with n plus 1 here. So this en is n plus half h cut omega minus n plus 1 plus half h bar omega. Let's just take this h bar omega common right here. Actually, this h bar cancels here, this omega naught becomes omega naught square. So we are left with q square e square 2m omega naught square. So here this n cancels, and we have plus 1 minus half cancels with this, so we are left with 1. So we have n plus. So over here we have n plus 1. So the half cancels with half, n cancels with n, we are left with minus 1. And this becomes q square e square 2m omega naught square. So this is n minus 1. So we are left with just minus 1, which means that en 2 is minus q square e square 2m omega naught square. So energy of the one-dimensional quantum harmonic oscillator are shifted downward by this amount when the harmonic oscillator is placed in the electric field. And you see the shift in energy or the change in energy is proportional to the electric field square. And if I want to show it symbolically, let's say these are different states. So when we apply electric field, these states, the gap between the states h bar omega remains the same, except because all the states shift downward with the same value, because none of this is dependent on n. So this is how we can use the non-degenerate perturbation theory to find the corrections to the eigenvalues of eigenenergies of different non-degenerate systems. By the way, this also tells us that there is no permanent electric dipole in an oscillating quantum harmonic oscillator, because if there would be one, then change in energy would be proportional to mu dot E, where mu is the electric dipole moment and E is the electric field, and the change in energy would be proportional to the electric field. However, the change in energy is proportional to electric field square, not to the electric field. But this actually presence of energy proportional to E square also indicates that this is sort of an induced electric dipole. Let me just briefly discuss this. For example, if you have something which is an electric dipole, and if you apply an external electric field, then the energy of this dipole is minus mu dot E, which, as you can see, is proportional to the electric field. However, we saw that there is no energy proportional to electric field, which means that this dipole is sort of acting as an induced electric dipole, because what is happening that there was no net electric dipole moment, but once we applied the electric field, an electric dipole moment proportional to this electric field was induced. So now our potential electric energy is minus mu dot E. Since this is also proportional to electric field, so we get this electric energy proportional to electric field square, because there is an electric field here, and then in the energy term there is an electric field here. So once our change in energies are proportional to electric field squared, we can deduce that thing which we are studying becomes an electric dipole moment once the electric field is applied. However, there was no prior electric dipole moment present, because if there was one, the energy would have been proportional to, the change in energy would have been proportional to the electric field. Anyway, so let's now study the Stark effect in hydrogen atom. Stark effect in hydrogen atoms, or hydrogen-like atoms. So our problem is like this, that we have some atom which is placed in an external electric field, but this time we are going to choose the axis of the electric field as z-axis. So our external electric field is pointing along z-axis, which means that our electric potential energy is minus E EC. This minus is because of the definition of potential energy. It's minus gradient of the force, because force is minus gradient of the potential energy, and this minus is because the charge on electron is negative E. So our potential energy is EC, which means that our Hamiltonian is H0 plus EEG, where H0 is our, so let me put a Z hat because this is an operator now, is E square 2 mu plus our whatever potential energy was, which was ZE square over 4 pi epsilon naught R. And since we don't need to worry about that, we have already solved our system for H0, and we know the eigenfunctions and eigenenergies of this H0 operator. All we now need to do is find the corrections to these energies once we turn on the external electric field, which is given by this perturbation term H1. And just to recall these H naught operator had this NLM states where the energy was only proportional, only dependent on N, where this is a quantum number which can be anything 1, 2, 3, 4, 5, so on, and this L has to be 1 less than N, and M goes from minus L to L. And as we have already seen, that this system, if we neglect the spin of the electron, which we are doing right now, is n squared degenerate. For example, for n is equal to 1, we have only one state. For n is equal to 2, we have 4 states. For n is equal to 3, we have 9 states, and so on. So it means once when we turn on the external electric field and we want to find the energy correction to the n is equal to 1 state, we can use the non-degenerate perturbation theory. And however, once we have to find the energy corrections in the n is equal to 2 states, we have to use the degenerate perturbation theory because this state is 4-fold degenerate. So let's do that now, and for that let me shift to the other board. Okay, so let's first find the energy corrections in the n is equal to 1 state. So we can use non-degenerate perturbation theory quickly. So E11 is 1, 0, 0, and this H1, 1, 0, 0, and this H1 is EEZ hat. So I can take this thing out like this. Well, you see, to compute this inner product, essentially I have to do this. There's a triple integral over psi 110 mod square, and since this z operator is nothing but just z here, and this volume element, if I'm doing, let's say, in spherical coordinate, is r square dr d theta d phi sin theta. However, an integration is over all space. That theta is 0 to pi, phi 0 to 2 pi, r is from 0 to infinity. And in principle, I can do this integration on x from minus infinity to infinity, y from minus infinity to infinity, z from minus infinity to infinity, and I can use this Cartesian volume element dx, dy, dz. However, independent of what coordinate system we choose for integration, there is one thing which is apparent right away. These psi's have definite parity, which means that they are either even or odd, because the Hamiltonian has definite parity. And once we take the square here, whatever the parity was, as long as it is definite, we get an even function. And now once I have multiplied with z, the overall function is now odd. Because for z negative, it is negative, for z positive, it is positive, which means that when we do integration over all space, because of this oddness of this function, the integration would be 0. If you want, by the way, you can do this integration explicitly as well, because you can substitute for z, let's say you substitute r cos theta, for y1 z psi 1 0 0, it's nothing but r1 0 y 0 0 mod square volume element dv, and these are simple functions. You substitute them here, you perform the integration, and you will still see that it is 0. if you don't want to argue from the oddity of this function. Anyway, so this means that first order correction is 0, and this also means that we can compute the second order correction, and the second order correction, since it's proportional to these terms in the series, we write them. Let's write it explicitly. The second order correction is sum over all n, l, m, except that n is equal to not 1. E10 minus E0. So essentially, we have to take the dot product, this term we have to evaluate for each NLM except when n is equal to 1, and sum for all of these terms. But since this is square present here, and this H1 is EEZ, so this will be proportional to E square. And as we were arguing for the 1D harmonic oscillator, this means that in n is equal to 1 state, this atom does not have any electric dipole moment. That's why the first order correction is 0, and its second order correction is proportional to A squared, which means that it can become an electric dipole once we place it in an electric field. So this is actually the property that gives rise to several forces, like even among atoms which are otherwise neutral, for example helium atoms or other atoms in noble gases, that let's say in helium atom the electrons are in s shells and the atoms have no interaction among them because there's no electric dipole. However, when they come closer, the one atom sort of produces an electric field in the other, which makes it an electric dipole temporarily when they are nearby, and sort of a bond can be created or interaction at lower temperatures. So this is n is equal to 1 state. Let's now see n is equal to 2 state, and since it's a degenerate state, fourfold degeneracy is there, we cannot use the non-degenerate perturbation theory, and instead we have to solve this matrix. But let me just say that let's label the states like this. Let me call psi 1 a state 200. Let's call psi 2 a state which is 210. Let's call psi 3 a state which is 211, and let's call state psi 4 a state which is 21 minus 1. So once we have these states, we need to compute these elements in this matrix. So this is a 4x4 matrix, and we have to find C1, C2, C3, C4 to find this En1. So before we can solve this matrix, we actually have to find all of these terms. So let's begin with H111. So H111 is this term, that H1 psi 1, psi 1. So psi 1 is 200 state, 200, H1, 200. Now this is a state like this, P, E, and this 200 state is Y, this is R20 Y00 conjugate, and for this there is Z. I'm taking E on outside, and for this it's R20 Y00 R square sine theta d theta d phi. Again, the same argument that we had here. This is an even function because of the square, because this can be written as Z into R20 Y00 mod square. So this is an even function, and because of the Z, this becomes an odd function. So odd functions integration over all space is 0. So I'm going to write it 0, but if you want, you can still do this integral explicitly. You can write R cos theta for Z and do this integration in spherical coordinate for yourself, and you can see that this indage is 0. So this is 0. Similarly, we can see that with the same argument, we can see that this H122 should be 0. Similarly, H133, H144, this is 0. And now we are left with the only off-diagonal terms, because all 4 diagonal terms are 0. Now, to evaluate off-diagonal term, even before we do that, let me just note one thing. We have already seen that Z, LZ commutes, that they're equal to this, which means that Z, LZ is equal to LZZ. Let's use this commutator relation for a very nice property that will help us determine those elements. If I apply this thing on, let's say, a state N, L, M, and take its L prime, M prime, here M prime, M prime, M prime, Z and Z, N, L, M. Since Z, L, Z, L, Z, Z are equal, this is Z, L, Z, and this is LZ. Now we know what LZ does to its eigenstate. It simply gives us mh bar. So this LZ, when operates here, it gives us mh bar, and we are left with this. Similarly, this LZ, when operating on this one, will give us m bar, m prime h bar, n bar L, m prime Z, and M. So this h bar cancels from both sides. If you bring it on this side, this and that term are the same, so we get m minus m bar, m prime into n prime, l prime, m prime, n, l, and 0. So either this or that are 0, which means that if m is equal to m bar, this is 0, and this may not be 0. Maybe or may not be 0, but we will have to evaluate it. However, if m is not equal to m prime, that m's are different, then this means that this is definitely n and m is 0. So it means when m's are different, then this is definitely 0. But when m's are same, we have to evaluate. Which now means that if I come back to this matrix here, these are already 0 because of their oddity in the integral. Now, this is the value of m written here. For psi 3, psi 4, for any product actually. You see this 2, 1 is the H1 interposed between psi 1, psi 2, and they have same M. And similarly for H1, 1, 2, they have same M, but for everything else the M is different. For 1, 3, M is different. For 1, 4, M is different. Similarly for 4, 1, for all other terms, M is different except for this one and this one. And we see that when M is different, this has to be 0. If it is 0 with the Z hat, it's definitely 0 with H1 here, because H1 is nothing but Z hat. So this Z operator thinks this is 0, H1 is 0. So it means now that in my matrix, I only need to evaluate this term, H1, 1, 2 term, which is nothing but 2, 0, 0, H1, 2, 1, 0, and I can write it like this. So this 2, 0, 0 is R2, 0, Y0, 0, H1 is E, and Z, let me write R cos theta in place of Z, and this 2, 1, 0 is R2, 1, Y1, 0, and R squared dr d theta d phi sine theta. This is our volume element, and we can easily evaluate this integral because we know R2, 0, Y0, 0, etc. So if you put these functions here, you can show that, which is actually part of your homework, that this comes out to be minus 3e a naught, where this a naught is actually Bohor's radius. We'll get h bar and other terms here, and if you collect them all, it is nothing but a naught. So this is H112, and similarly H21 is also this number, which now means that we have found our matrix, and it is 0 minus 3e a naught 0 0 minus 3 e a naught 0 0 0 0 0 0 0 0 0 0 C1 C2 C3 C4 and 1 C1 C2 C3 C4. So this is the matrix that we have to solve to find C1, C2, C3, C4 and En1. Okay, so this means, let me bring this thing on this side, which means that this En1 would be subtracted from these diagonal elements, because we can imagine that this is En1 into identity matrix here, 4 by 4 into this. So identity matrix has 1, 1, 1, 1 on the diagonal, and if you bring it on this side, this En1 will be subtracted from the diagonal entries, and our system of equation becomes minus En1 minus 3 E A naught 0 0 minus 3 E naught minus En1 0 0 0 0 minus En1 0 0 minus En1 into C1, C2, C3, C4 equals 0. Now for non-trivial solution, the determinant of this matrix has to be 0. And let me open that determinant by the first row. If I open it by first row, I get minus En1 minus 3. So I get this part here, minus En1 0 0 0 minus En1 0 0 minus En1, then minus into minus this, so this is plus 3 EA naught. So this row and this column goes away. I have minus 3 EA naught 0 0 0 minus this 0 minus En1, then 0 0 this 0 0 minus En equal to 0. Now this is a diagonal matrix. This is a diagonal. This is a determinant of a diagonal matrix. This is determinant of a diagonal matrix. So it's easy. Its determinant is simply this into this into this. So minus into minus into minus and into this. So this is 1 2 3 4 minus. So I get En1 power 4 plus actually minus. So its determinant is minus in this into this into this, so I get to minus 3 EA naught square into En1 square is equal to 0. So let's take En1 square common, so we are left with En1 square minus 3 EA naught square is equal to 0. So it means our roots are this En square is equal to 0. So I have En1 equal to 0 and 0. So it's square. So there are two eigenvalues. Both are 0. And then from here, when we put this equal to 0, we get En1 equal to, so this goes to the other side, becomes plus. Its square root would be plus minus 3EA. So finally, we got 4 eigenvalues, 4 corrections to the energies, because we had 4 states to begin with. So all of them had the same energy. But now we see that the 4 corrections are 0, 0. So it means we get 4 new states, but 2 of those states still have the same energy, which was previous one because there is no correction. And the other 2 states have different energy from the previous states. And the difference is that one has a higher energy and the other one has a lower energy by this amount 3 EA naught. And we also need to see what are the new states. So to find new states, we have to plug in each of this eigenvalue in this equation and find C1, C2, C3, C4. So let's first do it with the energy correction 0. So if I put 0 for E and 0 everywhere, we get 0 minus 3 EA naught 0 0 minus 3 EA naught 0 0 0 0 0 0. So the first row gives us minus 3 EA naught C1 equal to 0. The second row gives us minus 3 EA naught C2 equal to 0. And this is 0 equals 0, 0 equal to 0. So these two equations tells us that C1 is 0 and C2 is 0. Which means that for the 2 states that corresponds to En0, that they still have the same energy. They are not a mixture of psi1 and psi2, where, let me just repeat that psi1 was 2 0 0 and psi2 was 2 1 0 and psi3 that we have just used as label 2 1 1 and psi4 we chose 2 1 minus 1. So it means that, and since C3 and C4 can be anything, so this didn't give us any information on C3, C4. It means the 2 new states which still have the same energy because correction is 0, they are either Psi3, Psi4 as it is, are any linear combination of these two states, but they don't involve these two states at all. Okay, so let's now see what happens for plus 3e a naught. So for this, our matrix becomes 3e a naught minus 3e a naught 0 0 minus 3e a naught 3e a naught 0 0 0 0 3e a naught 0 0 0 3e a naught psi 1 c2 c3 c4 equals 0. So the first row gives this into C1 minus this into C2, but this thing is common, so I get C1 minus 2. The second row gives us C1 plus C2. The third row gives us C3 equals 0, because only this into C3 have to equal to 0, and this is a constant. So C3 is 0, this gives us C4 0. And both of these equations give us that C1 is equal to C2. And let's say there's some C. So if there's some C, it means that the state that corresponds to this is a linear combination of psi 1, psi 2 with the same value. So C into 2 0 0 plus 2 1 0, and since these are normalized state, if you normalize this one, C comes out to be 1 over 2 under root. So you get 1 over 2 under root 2 0 0 plus 2 1 0. So it means these two states mix to give rise to another state when you switch on electric field, external electric field, and the energy of this state is higher than the energy of both of these states by an amount 3e a naught, because the new state is the mixture of these two. By the way, if you do the same thing with the minus 3e a naught, you put minus here, then C1 will be minus C2, and you'll get the similar expression but with a minus sign here. So if I summarize this thing, let's say over, let me do it here, that before we turned on electric field, we had 4 states and all of them had the same energy. But once we turned on the electric field, this is n is equal to 2 state. Two of the states still have the same energy, but the other two, they mix to give rise to 2 more states. So this is that 2 0 0 plus 2 1 0, and this is 2 0 0 minus 2 1 0. Of course, there is a 1 over 2 here, there is a 1 over under 2 here, but the energy of this state is higher by an amount 3e a naught from this state, and the energy of this state is lowered by the same amount. So degeneracy, that you see a couple of things have happened. When we applied the electric field, the degeneracy is lifted partially. That 4 degenerate states now give rise to 3 energy levels, and these 2 states are now non-degenerate, but the 2 states are still degenerate. The second thing that has happened is that the change in energy is proportional to 3e a naught, which is proportional to just the magnitude of electric field. Which means that the 2 0 0 and 2 1 0 states have an electric dipole moment present in the absence of electric field. So that's why when we turned on the electric field, then energy change quickly, because the change in energy due to external electric field of our electric dipole is mu dot E, which is proportional to E. However, these two states does not have an electric dipole moment in the presence of, in the absence of external electric field, and we can only know if the electric dipole is induced or not if we compute the second order correction and see if that is proportional to E square or not. Okay, so this is how we can use the degenerate perturbation theories to compute degenerate and non-degenerate perturbation theories to compute changes in energy. And just to recap, when we had n is equal to 1 state, the energy changed, the first order change in energy was 0, the second order energy change could be proportional to E square, but we were able to compute it using non-degenerate perturbation theory. But these changes in energy have to be computed using the degenerate perturbation theory. Thank you.